The obvious solution to this problem is to vary not only excitation frequency, but also applied voltage magnitude, such as volts per hertz control. Volts per hertz control proportionally lowers applied voltage at excitation frequencies below the base frequency. At the base frequency and beyond, up to maximum, full voltage is applied. In summary, given low voltage magnitude at low frequency, the current stays low. When excitation frequency is increased, inductive reactance and CEMF increase, therefore opposition also increases, allowing increased voltage to be applied, still keeping current inside the intended operational range. A basic graph of volts per hertz control is typically linear from 0 to the base frequency, although as we'll soon learn, this isn't always the case, and sometimes application-specific volts per hertz profiles exist. This basic linear volts per hertz profile for a generic motor drive applies 0 volts at 0 hertz, and assuming a 60 hertz base frequency, full voltage at 60 hertz. If one was to dial the excitation frequency down to half the base frequency, or 30 hertz, applied voltage would also be proportionally reduced to 50%. Beyond the base frequency, motor drives typically flatline applied voltage at 100% up to the maximum frequency. Linear means of volts per hertz control is not the only volts per hertz profile available. For example, consider a reduced torque application where the volts per hertz profile is, for lack of a better descriptive term, a concave quadratic. At the base frequency and up to maximum, full voltage is still applied. However, for excitation frequency conditions below the base frequency, less voltage is applied than the previous linear volts per hertz method. Such a volts per hertz profile could be used for an application that really needs a gentle start. Depending upon the features incorporated in a particular motor drive, other application-specific volts per hertz profiles may exist. Consider this dual slope increased torque or torque boost profile, where applied voltage increases at a steeper slope up to a certain transition frequency, beyond which the slope decreases. As previously, upon reaching the base frequency, full voltage is applied. Such a volts per hertz profile could be useful for a load with a large initial static inertia or friction. Let's say yanking your lazy lad partner off the couch. This dual slope volts per hertz profile has a notable knee, defined by a point which I'm calling the boost frequency. As implied by the title, voltage is boost at the boost frequency. The amount of boost voltage and the boost frequency value can be expressed directly or as a percentage above the normally linear applied voltage in base frequency. Both these values are often user adjustable. For example, consider a motor drive with a base frequency of 60 Hz, a maximum frequency of 100 Hz, making use of 120 volt line to neutral, 208 volt line to line 3-phase AC, using a dual slope increased torque profile where the motor frequency is 30% of base frequency and boost voltage is plus 20% above normal linearly applied voltage. In this scenario, the boost frequency is 30% of 60 Hz or 18 Hz. This calculation is simple enough. Boost voltage takes a little bit more figuring. Given a typical linear volts per hertz profile, a frequency of 30% of base frequency would ordinarily experience an applied voltage of 30% of full voltage. However, we're boosting it by an additional plus 20%. In this case, applied voltage would be 30 plus 20, or 50% of full voltage, for a value of 60 volts line to neutral, 104 volts line to line at the boost frequency. Between 0 Hz and the boost frequency, applied voltage is linear. As is between boost frequency and base frequency, it's just that they have different slopes. Hence the title, dual slope volts per hertz profile. For this current configuration, an excitation frequency of 9 Hz would most likely experience 25% of full voltage, and an excitation frequency of 39 Hz, midway between 18 and 60 Hz, would most likely experience 75% of full voltage, or 90 volts line to neutral, 156 volts line to line. More complicated volts per hertz profiles may exist depending upon the features incorporated by a particular manufacturer. For example, consider this dual slope combination of a linear volts per hertz profile and a concave quadratic for special reduced torque applications. This volts per hertz profile is linear between 0 Hz and a certain transition frequency, beyond which it's concave quadratic up to the base frequency, beyond which it flatlines at 100%. Again, the complexity of volts per hertz profiles can range from the simplest fixed linear profiles defined by a base frequency only, or an extremely application-specific curve depending upon the functionality offered by a specific motor drive. Alright, that's really about it for volts per hertz control. However, before we bring this lecture to a close, let me make a brief comment about units directly related to an upcoming lecture on acceleration and deceleration profiles and ramp times. Volts per hertz profiles, as implied by their titles, are graphs of applied voltage as a function of frequency. As I alluded to during the introduction, motor drives can perform soft starts and soft stops by varying both applied voltage and excitation frequency over time. Note the dramatic emphasis I'm placing on the qualities voltage, frequency, and time. This suggests a third dimension needs to be added to our analysis. This may initially seem overly complicated for two-dimensional thinkers. However, it's actually pretty easy if you just use two separate graphs. For example, consider a motor drive with a simple linear volts per hertz profile up to the base frequency, and another plot where excitation frequency is ramped to 100% of the base frequency over an adjustable acceleration time of, let's say, 10 seconds. Assuming a 60 Hz base frequency, this means when excitation frequency is ramped from 0 to 60 Hz over 10 seconds, voltage is also ramped from 0 to 100% over the same 10-second period. At 5 seconds into the ramp-up event, excitation frequency is 30 Hz and applied voltage is 50%. When the ramp-up event finishes at 10 seconds, excitation frequency flatlines at 60 Hz, as does applied voltage at 100%. This method is a little bit more complicated when you're using a more complicated volts per hertz profile, and as we'll learn, a more complicated acceleration or deceleration profile. However, it's still easy if you use two graphs. Given a dual slope torque boost volts per hertz profile with our previously established values of a plus 20% boost to 18 Hz, and the same linear acceleration profile where excitation frequency is ramped to 100% of the base frequency over an adjustable acceleration time of 10 seconds, we can calculate applied voltage and excitation frequency at specific times. For example, if it takes 3 seconds to ramp up from 0 to 18 Hz, it takes 3 seconds for voltage to go from 0 to 50%. It then takes the remaining 7 seconds for excitation frequency to go from 18 to 60 Hz, at the same time applied voltage goes from 50 to 100%. Like I said, we'll examine acceleration and deceleration ramp rates and profiles in later lectures. In conclusion, this lecture took a brief look at volts per hertz control for generic motor drives. We defined base and maximum frequency. We learned motor drives not only vary excitation frequency, but also applied voltage for excitation frequencies below the base frequency. Additionally, we examined simple linear volts per hertz profiles and more advanced quadratic, dual slope, and special purpose volts per hertz profiles for reduced or increased torque applications. Finally, we previewed how volts per hertz profile must be used in combination with frequency as a function of time plot during acceleration and deceleration events. Remember to review these concepts as often as you need to really drive it home. Imagine how well lab will go if you know what you're doing. Thank you very much for your attention and interest, and we'll see you again during the next lecture of our series. Remember to tell your Lazy Lab partner about this resource. Be sure to check out the Big Bad Tech channel for additional resources and updates.